Bismillahirrahmanirrahim. I am Dr. Amir Badshah, lecturer in Department of Chemistry, Cohort, University of Science and Technology. Today the topic of our lecture is nucleophilicity and basicity, and along with them we will discuss E1cB reaction 2. This is lecture number 17 from the course Organic Chemistry 2nd, having code Chem 322. The outline of our lecture include introduction, then followed by nucleophilicity. After nucleophilicity we will discuss basicity, and then the various factor which is affecting nucleophilicity as well as basicity, and at the end we will discuss E1cB types of reactions, and we will mention also some references from which this lecture has been taken. First, what is nucleophile? Before discussing nucleophilicity, we should know about the nucleophile. Actually, nucleophile are electron-rich species which are capable of donating of electron. It has not only electron, but it is capable of donating electron. Then such species are called nucleophile. This definitions that it has electron and it is capable of donating electron is like that of the definition of the Lewis base. Lewis base has also electron and they are capable of donating electron. But in case of nucleophile, the nucleophile attack on the carbon deficient center. If a species having electron, maybe in the form of negative charge or maybe in the form of lone pair of electron, attack on electron deficient center, and that electron deficient center is carbon, then such electron rich species is called nucleophile. But if this electron rich species attack on hydrogen atom or proton, then such type of electron rich species is called a base. Now, what is nucleophilicity? Actually, nucleophilicity is a rate phenomenon, or you can say it is a kinetic phenomenon in which a nucleophile attack on a electrophile. So if a nucleophile attack at a high rate, then we can say that the nucleophilicity of the nucleophile is higher. If it react at a slower rate, then we can say that the nucleophilicity of the nucleophile is low. So a nucleophilicity is totally a kinetic phenomenon. It means it deal with speed, or you can say it deal with the rate. It doesn't deal with instability of the reactant or the product. That it at the attack of nucleophile we will get a species that may be stable or not. Nucleophilicity doesn't deal with that. It only deal with the rate, that how much quick or how much fast or slow a nucleophile attack an electron deficient center. On the other hand, basicity is a thermodynamic phenomenon. It refers to the position of equilibrium. It is an equilibrium phenomenon. It is not a rate process like that of nucleophilicity, but it is a stability phenomenon in where there, if in equilibrium and exist, then in equilibrium will favor that side in which a weak base is present. For example, it has been shown here that this is a base here because it attack on the proton, so it acts as a base, is a result of which we can get water and a weak base. So that's why this equilibrium is shifted toward that side, because here a weak base is present. Now we are coming to the factors which are affecting nucleophilicity. Number first is the charge on the nucleophilic center. A nucleophile which has a negative charge will be a stronger nucleophile than which has a lone pair of electron. For example, if we have OH which has a negative charge, and on the other hand if we have water, so in both cases we have hydroxygen, but in that case, in the first case here it has negative charge, in the second case it has lone pair of electron. So a nucleophile which has negative charge will be stronger nucleophile than that one which has lone pair of electron is shown here. This is a strong nucleophile and this is a weak nucleophile, because here oxygen has negative charge and here oxygen has lone pair of electron. The second important factor is the polarizability. First we should know what is polarizability. It is actually describe us the distribution of electron unevenly is a result of external influence. For example, this is an atom where the electrons are symmetrically distributed, but under the external influence, when this electron is unevenly distributed, on one side the electron density is more and on the other side the electron density is less. This uneven distribution of the electron due to some external influence, it is called polarizability. Polarizability depends upon on the size of the atom. More specifically, when the size of the atom is larger, then the polarizability will be more. If the size of the atom is small, then the polarizability will be less. And especially it is depend upon the size, but along with the size it is especially depend upon on the number of electrons, that how much away it from the nucleus. Is much the electron are away from the nucleus, then the polarizability will be higher. Polarizability even it is more important than the charge. For example, here this sulfur is present, and lone pair of electron is present on the sulfur, and here lone pair of electron is present on the oxygen. Here the H2S is more nucleophilic than water. What is the reason? Although the electron density is more here, the electron density is less, but here the polarizability is more. Why? Because sulfur has larger size than oxygen, so due to large size, sulfur has more polarizability than oxygen. The next factor is among the polarizability, as we have discussed, that polarizability is more important than the charge. How it is more important than the charge? Actually, it is a relationship between the polarizability in the nucleophilicity. If a species is more polarizable, then it will be more nucleophilic in nature. For example, here hydride ion has a negative charge, but still it doesn't act as a nucleophile. Although it has a negative charge, the reason is that because it is not polarizable. So polarizability in nucleophilicity has a very important relationship. If a species is polarizable, so it will be more nucleophilic compared to a species has a negative charge. It has a negative charge and plenty of electron, but still it doesn't act as a nucleophile. The reason is that because here the charge is not polarizable. The third important factor is the salvation factor. The salvation factor is the factor which is more important than the charge. The reason is that because here the charge is not polarizable, so it will be more nucleophilic. The reason is that because here the charge is not polarizable. The third important factor is the salvation factor. The salvation factor is the factor which is more important than the charge. The reason is that because here the charge is not polarizable, so it will be more nucleophilic. The third important factor is the salvation factor. Actually, when a nucleophilic substitution is carried out, a solvent is used, and that solvent has a marked effect on the nucleophilicity of the nucleophile. For example, if we use a polar aprotic solvent, then an anion is weakly solvent. For example, if these anions are present which act as a nucleophile, so if we use a protic solvent will not solvate it, or it will solvate it but weakly. So in that case, these nucleophile will be free for attack, and thus here the basicity is dictated nucleophilicity. It's mean that here the nucleophile, here these anion will show high nucleophilicity. That's why the fluoride ion is more nucleophilic than chloride, and chloride ion is more nucleophilic than bromide, and bromide ion is more nucleophilic than iodide. But if instead of a protic solvent we use a protic solvent, it should be polar. Here is polar 2 and here is polar 2, but here it is aprotic and here is protic solvent. If we use a protic solvent, then it will highly solvate the anion. If it solvated the anion more, so it will not free for the attack, and thus in this case the polarizability dictate nucleophilicity. In the former case, the basicity dictate nucleophilicity, but here the polarizability dictate the nucleophilicity issue. Here, in that case, that process that is reversed here. That trend is reversed here. Here the iodide is more nucleophilic than bromide and chloride, and so on. Why? Because here fluoride ion is more solvated compared to the chloride ion. If it is more solvated, then it will be less free to be attacked. So that's why its nucleophilicity is low. It's mean that the nucleophilicity depends upon on the solvent which is used. If we use a protic solvent, then in that case the anion is free, and if we use polar protic solvent, in that case anion is not free. The other factor, the fourth factor, is the steric effect, that how the size of the nucleophile can affect the nucleophilicity. Actually, a nucleophile has, if a nucleophile has a bulky size, it means large size, its nucleophilicity will be low. For example, tertiary butoxide, which has three alkyl group, which has three, for example this is tertiary butoxide, these are alkyl groups, and on the other hand one is the ethyl oxide, CH3 CH2 and O negative. Here the size of the tertiary butoxide is larger compared to the size of ethyl oxide. So according to our previous knowledge, this species should be more nucleophilic than that one, because the size of this species is big one, but still the ethyl oxide is more nucleophilic than tertiary butoxide. The reason behind this is that because this is bulky in size, and this is small in size, so this, due to bulky nature, it cannot easily approach to the electrophilic carbon, and ethyl oxide can easily approach to the electrophilic carbon. So that's why ethyl oxide is more nucleophilic than tertiary butoxide. Although if we compare them by the basicity, In that case, the basicity of the nucleophilicity of tertiary butoxide is less than the nucleophilicity of ethoxide. But however, if we consider the basicity of tertiary butoxide is more than the basicity of ethoxide. The main reason behind this is his bulky size. The next topic is the factor which are affecting basicity. Actually, the strength of a base depend upon on the strength of its conjugate base. If the conjugate base is stronger, then the base will be weak. If the conjugate base is weak, then the base will be stronger. It means there is an inverse relationship between them. For example, chloride ion, it has a lower and it has low basicity. What's the reason behind that? Because its conjugate base, it's Cl. It's a very strong. So if it is strong, then the chloride ion will be weak. Now, what are the factors which is stabilize the negative ion? Here, this negative ion on the conjugate base, when it is weak or when it will be stronger one. If it is stable, then it will be weak. If it is not stable, then it will be strong. So what are the factors which stabilize them? So we will discuss them here in detail. Number first, we can find that which atom has a negative charge. If in a period wise, if the negative charge present on the atom on the left side in the period, that will be less stable compared to the atom which is present on the right side. What's the reason of it? The reason of it is the electronegativity of the atom. For example, here the negative charge is present on the carbon, and it is formed from what? It is formed from this species where hydrogen is present. When the hydrogen is abstracted, so it is from this one. In this is formed from the alcohol, this species hydrogen and oxygen, and when it lose this hydrogen, so it form this conjugate base and it form this conjugate base. Now which one is stable? As we have mentioned here that it is present on the position of the element in the period. Carbon is present on the left side in the period in the periodic table, and oxygen is present on the right side. So the element which has negative charge in that element is present on the left side, and that will be less stable. What's the reason? The reason is that of electronegativity, because carbon is less electronegative than oxygen. But if in case of column we consider, then the dominant factor is not electronegativity, but here the dominant factor is that of size. For example, if we consider OH, for example, it is obtained from the by donating oxygen, hydrogen, and this species is formed, and this species is formed from by donating of hydrogen by H2S. When H2S donate a hydrogen, it also form this conjugate base. So in this case, the negative charge is present on the oxygen, which is a more electronegative than sulfur, but here the sulfur size is greater than the size of oxygen, and compared to electronegativity, the size effect is more dominant. So that's why here the SH which has negative ion, this one is more stable than the hydroxyl ion. Although oxygen is more electronegative and it can attract this electron, but here the negative charge is more stabilized because the sulfur size is higher, so electron will distribute it on the whole size of the sulfur and the electron density will be reduced. The second important factor is the resonance. The resonance can tell us. In the former case, the atoms were different on which negative charge were present, but in this case, the atom are the same. Here oxygen is present and here oxygen is present too, but in that case, this species is more stable than that one because here negative charge is limited only to oxygen atom, but here the negative charge is stabilized by resonance. It transfer here, then it is transfer here. So here the negative charge is stabilized. If it is stabilized, so it will become more stable. In here the negative charge is concentrated only on oxygen. It is limited to oxygen. It means there is no resonance, so it is less stable. The third factor is the induction factor. For example, here one group was alkoxy group and the other is the carboxylate group. If both of them are carboxylate group, here negative charge is also stabilized by resonance, and here negative charge is also stabilized by resonance. So which species will be more stable? Then induction can decide. Here there are three hydrogen atom attached to this carbon, three hydrogen atom attached to carbon atom, but in the other case these three hydrogen has been replaced by chlorine, and chlorine is more electronegative. If it is more electronegative, so it will drag this negative charge toward itself and will increase its stability. So here induction make them more stable. Here there is no induction, so it is less stable. The fourth factor is orbitals. For example, here this carbon is sp2 and this carbon is sp. So here negative charge present on the sp2 carbon and here negative charge is present on the sp, and we know that the sp carbon has greater s character compared to the carbon which has sp2 hybridization. So that's why this species is more stable compared to the compared to this species, because here the negative charge is present on the sp3 carbon and here the negative charge is present on the sp2 carbon. And this is the device that we will first look to the atom. If negative charge is present on a more electronegative atom, then that will be the more stable one. If atoms are the same, then we will look to the resonance, because here in the resonance, and if in both cases there are resonance too, then we will look to the induction. The my goal are the species or the negative charge species has induction, then that will be the more stable. And the last one is the orbitals. If all factor cannot decide, then we will look to the orbital. If orbital is speed and that carbon has negative charge, then it will be more stable than that one which has sp2 carbon. So this is a device which is called RU device. Nucleophilicity versus basicity. So there are some species which can act only as a nucleophile. For example, halide. These species can act only as a nucleophile. Similarly, H2S, RSH, and similarly the negative sulfide ions and alkyl sulfide ion. These species always can act as a nucleophile. Similarly, some species can act only as a base. For example, the hydride ion and DBN and DBO, where DBN is derivated from 1,5 is a bicyclo 430 non 5-ene. This is the structure of this compound. So DBN is abbreviated from this structure, and DBU is also 1,6-diisobicyclo 540 undic 7-ene. So hydride ion, which is derived from the sodium hydride, in DBN and DBU always act as a base. It means these species will always obstruct hydrogen ion, and these species will always attack on the electrophilic carbon center. Some species can act both as a base as well as a nucleophile, and they are strong. For example, hydroxyl ion, methoxy ion, ethoxy ion, and tertiary butyroxide. So these species can act as a nucleophile as well as a base. These species can also act as a base as well as nucleophile, but these are the weak ones. For example, H2O, for example, methanol, and for example, ethanol. These are the comparison between the substitution versus elimination reaction. If the reagent can function only as a nucleophile, as we have discussed in the previous slide, then if the substrate is the primary one and the species used can act as only nucleophile, definitely substitution reaction will take place, nucleophilic substitution reaction will take place. But if the substrate is primary, then SN2 reaction will occur. And if the substrate is secondary, then there are two possibilities, SN2 as well as SN1. If the substrate is tertiary, then there is only one possibility, and that one is the SN1 reaction. If a reagent that function only is a base, then for example hydride ion, for example DBN, so in that case if the substrate is primary, it will favor E2. If the substrate is secondary, it will still favor E2, and if it is tertiary, then still it will favor E2. If a reagent can act both as a strong base as well as a strong nucleophile, for example alkoxy and hydroxy, in that case if the substrate is primary, then both the possibility of E2 and SN2, but the SN2 will be the major one. And similarly, if the substrate is the secondary, then both E2 and SN2 mechanisms are possible, but in this case E2 will be the major one. But if the substrate is tertiary, then in that case wholly solely the reaction will be follow E2 mechanism is shown here. The rate depend upon on the substrate. If it is primary, then both SN2 and E2 are possible, but the rate of SN2 will be higher. If the substrate is secondary, same is the case, both in SN2 and SN1 are possible, but E2 will be higher compared to the SN2. And similarly, if the substrate is tertiary, both E2 and SN2 are possible, but SN2 will be not possible here, and E2 will be only possible at a very high rate. If the reagent is a weak, can act as a weak base as well as a weak nucleophile, then if the substrate is primary, then SN2 and E2 are possible theoretically but not in practical. Similarly, if the substrate is secondary, then all SN2, SN1, E2 and E1 are possible theoretically but not practically. But if the substrate is tertiary, then both SN1 as well as E1 reaction is possible. The last topic is the E1cB reaction. We know previously that In the E1 reaction, first nucleophile, which is also called leaving group, leave first, and then hydrogen is leave in the abstracted in the following step. In the E2, both nucleophiles are leaving group and hydrogen leave at the same time. There is a third type of mechanism which is called E1cB, E1 elimination unimolecular conjugate base. It is abbreviated from that, where hydrogen leave first. In that case, nucleophile leaving group leave first and then hydrogen. And then in this case, both both leaving group and hydrogen leave at the same time, but here hydrogen leave first and then nucleophile. This reaction actually takes place in the two steps. In the first step, a carbanion is formed, so that's why it is sometimes called carbanion mechanism too. The first step is the first step. Here the OH species, which is a base, abstract hydrogen and form a carbanion, and this is the first reaction. And in the following, why it is fast, although a negative charge bound, because it is stabilized here. Negative charge shift here and this shift here, so it is stable one. So if a stable species is formed, then this reaction will be fast. And that step, in this step, the negative charge shifted here, and the leaving group will leave in the second step. So this is a slow step, and we get this species. So two steps are there. Number first step, abstraction of hydrogen, hydrogen abstract first, and the second following step, the leaving group leave, and we get the resultant product. The conditions which are necessary for the E1cB mechanisms include that the hydrogen at position beta to the leaving group should be acidic in nature. If it is not acidic in nature, then E1cB mechanism will not occur. Second is that there should be some stabilizing group which stabilize the negative charge on the carbanion. If there is no stronger attracting group, or the group which stabilize the negative ion are not present, then this reaction will not occur. The third one is the presence of leaving group, but the leaving group should be poor. It's not easily detached. It cannot easily lift. Then this reaction, if it is a good leaving group, so it will not follow E1cB mechanism. What are the kinetics? Actually, the rate depend here on the carbanion, as we have discussed in the previous species, that in the first step carbanion is formed, in the carbanion is formed, and then the carbanion is converted into final product. So only carbanion is involved in the rate determination step, so rate depend only on the concentration of the carbanion. But this carbanion is indirectly depend on the molar concentration of the base which is used for the formation of this carbanion in substrate. So in that case, rate depend upon on the substrate as well as on the molar concentration of the base. But the rate determination step is second step, having only one species, which is that is carbanion. So that's why it is called E1. It's mean unimolecular conjugate base. So only one species involved in the rate determination step. So that's why it is called E1cB mechanism. These are the references from which I have taken this lecture, and if you have any question about this lecture, you can contact me through WhatsApp or email. And thank you for watching this video.